All right, so today we're talking about logarithms. Later we will be talking about logarithms and exponentials. But one thing, I will deal with them on different days. But the logarithm is an interesting operator. First of all, you'll be hearing me talk about operators a lot. Operator is nothing more than a in math. Okay, an operator is an action. If you add two things, that's an action. Divide two things, square something. When you were dealing with basic algebra, if you were dealing with well, the x is being acted upon by the square. It is the operation of taking the square of that x. If I wanted to get rid of that square, what would I do? You take the square root. The square root is the inverse operator for the square. All the operators that you're going to be dealing with, and there are a lot of them, inverse operators. Fraction, multiplication is division, squares is square roots, logs and exponentials are inverse operations. So what happens is that I apply an inverse operator to both sides, keeping the fact that, and we'll talk about why plus and minus has to occur. I think we all know, but there's a class of operators that are called lossy operators, where you lose information whenever you use them. And an inverse, by the way, the square root of 10 is approximately pi, just for the record. All right, so one thing that I want to get through to you is that operations, and they have specific sets of rules. A logarithm is a nice operator because what a logarithm does is considered a step-down operator, okay? All right, a step-down operator is, you won't deal with that term until you get into quantum mechanics. But step-down operators are operators that take one operator and bring it down to the next level below it. So for example, what a logarithm turns exponentiation down to multiplication, and multiplication down to addition. Okay? Because addition is nothing more than rapid counting. Multiplication is nothing more than rapid addition. Exponentiation is nothing more than rapid multiplication. And yes, there is something above, there is rapid exponentiation. It's called tetration. We won't ever get there. Tetration is when you put a power to a power a certain number of times. So for example, if I wanted to do the tetration of 3, for example, that gets big real fast. Or not, but they're fun. Okay. They get really fast. They grow enormously. They're fun nonetheless. Okay. So logarithms are nice. A guy named Charles Napier came up with them, a million years ago, and what he was looking to do, his goal, was to try and find a way to multiply really big numbers really fast. So, you are trying to navigate by the stars, you're, doing all these calculations, your life depends upon it because you're in the middle of the ocean, and there's a storm, you're working by candlelight, and you don't have a calculator. Trying to multiply two 6-digit numbers together and messing that up could result in unpleasant things like death. Okay, so if there's a faster way to multiply these numbers, then that's wonderful. So what he did was he figured out that he could come up with these tables, and he could look up the number that if he's multiplying A and B are both big numbers. He looks up A, and he finds this other number, small number. And then he looks up B, he finds this other number. And instead of multiplying together, he adds those two. And by adding those two and then going backwards through the tables, he could find out what that one big multiplication would have been, because addition is a lot faster than multiplication and less error prone. So there are 8 rules for logarithms. Go into them all. All right. So the first is the definition of a logarithm. All right. Now this one is the one that you absolutely need to know, and if you know nothing else, this is the one you need. The definition. If log A of B is equal to C, then A to the C is equal to B. Now, all right, it's called the base of the logarithm. If it is not written down, it is assumed to be a 10, okay? There is one other fancy base. It's the natural logarithm. We will talk about that later, and its base is another fancy number, but we'll get there in due time. And that one doesn't use the word log, it uses ln. You'll see that on your calculator, okay? But again, we'll get there. Now, what the heck does that mean? So, if you'll bear with me, I'm going to be skipping, just like I did with the other notes. There's like one page that's like super critical, and we're going to come back and forth to it. This page is the supercritical page. We're going to come back and forth to it. So let's use some examples of that. So log base 3 of 81 equals x. So what the principle of logarithms tells us is that this says that 3 to the something is and what x be in this situation? 3 to the what gives me 81? 3 times 3, maybe a little bit less. 3 to the 4th, 9 times 9, right? 3 squared times 3 squared, 3 to the 4th. Now, so also you could say things like 5, whoa, that's a big one. We're going to wait on that one. I'm in the wrong order. Let's go backwards. Fluffy, what are you doing? My computer's misbehaving. So 5 to the x equals 125. And 125, this is where your factor trees come into play. If you can do a factor tree, fantastic. 5, 25, 5. So x is equal to 3. Okay? Also, give you something in exponential form like this. You need to be able to turn that into logarithm form. So this is currently in exponential form. Putting this into logarithm form would be this. Okay, so the x shrinks down and the 5 and 7 switch places. See how that works? Visually. So if I gave you a to the b equals 6, what would that look like in a logarithmic form? Log base a of 6 is how you would say it. Okay? All right, so flipping back and forth between exponential and logarithmic form is important. Okay? Now, there are rules of exponents, and all of our rules for exponents have a analog in the logarithms. Okay? So, next one we're going to see is arguably the one that you're going to use the most, which is log base anything, call it a, I don't care, of b to the c. Okay? So b is to the c power. Okay? So I'm going to move, it doesn't much matter. Usually that doesn't much matter. Let's put that on the inside. Okay, so just so that you know that b is to the c power. What this does is that this is where that step down operation becomes really nice, because that exponent is currently describing the process of exponentiation, obviously, since it's called an exponent. What it does is it moves out in front and becomes a coefficient. Okay, now where the heck did that come from? Because, well, it almost looks like, all right, Gronk, I think you're just making this stuff up as you go along. Well, that might be true for 99% of the stuff that I teach you, but this one I actually have a reason for. So if I had this, whatever the heck this is, I don't know, but whatever it is, it's equal to something. Let's just call it x. Okay? Well, according to the rules of logarithms, by the definition, this says a to the x is equal to b to the c. Right? Agreed? All right. Well, now if we think about this for a second, what's really going on? I have this, I've got this, that if I can take what was a high order operation and bring it down to be multiplication, then my become easy. Hold on to this for just a second. I'm going to, hopefully, if we get to it. 2, 3. Was exponentiation becomes multiplication. What is multiplication becomes addition. All right. And the reason for back down to, again, have a to the b c, that's really power of c. And using my logarithm rules, log both sides. What's wrong? What? Are we okay? Okay. You just look pretty suspect over there. All right. Moving on. Log base A of B over C. Well, what was multiplication became addition, so what do you think division? Subtraction. Okay, now these are the four that become basically of logarithms. These are the four that you use the most. There are two identities that you need to know. 5 log base A of A. And this makes sense if we apply the definition. A to the 1 is equal to A. See? Using the definition, the little baby A blows up to become an adult. The 1 hops over, becomes its exponent, and whatever is inside the logarithm comes out in front. And 6. Now let's look at this for a moment. A to the what? A to the 0. All right, so this immediately says to us, wait a second. Is this always true? Is anything to the 0th equal to 1? Everything but 0. This tells us right away that A cannot equal 0. Okay? Now, let's go back up here to 5 for a second. What would it look like if we had hold on. Where do I fail? For a second. Let's go up to the definition for just. Let's say what would happen if a were a negative. Let's see if it was. Let's make it of say 10. Or even better, something that is a power. Let's take 9. If we're looking to solve that, okay, using the definition of a logarithm, we run into a problem immediately. What is x? 2, right? Fine. Here's the problem. What happens now? Well, 3 times 3 times 3 is 27, right? But negative 3 times negative 3 times negative 3 is a negative 27. So negative bases become a problem. And in fact, we can't have a negative base just for this reason. Non-whole, with numbers that aren't whole numbers, or not explicit powers. You're dealing with a negative fractional piece. Does it change the sign or not? And now all of a sudden you like logarithms, and that's some crazy stuff. But if anybody is looking to do an awesome IA, roll into negative logarithms, imaginary logarithms. So no. They don't exist in the real numbers. They are not defined for negative numbers. And in fact, the graph, the domain of a logarithm is, it doesn't include or negatives. Okay. So the domain of any log is x greater than 0. Can't be 0, can't be negative. All right? We cool? Almost. All right. So, where'd my rules go? What? Did I delete a slide or something? Yeah, I guess I did. All right, well, that's fine. Got it back now. All right. So 5 and 6 are very, very useful, and you are trying to do some crazy algebraic things like that. So, if you're trying to combine things and you're dealing with whole numbers and stuff like that, these are very useful. Okay? But the next two are very useful in solving of equations. A to the log base A of B is equal to B. So if I have a log with a base of A, and I want to destroy the log, if I'm trying to get rid of a log, this is how I get rid of a log. Okay? For example, if I have log base 5 of x plus 2 is equal to 3. Okay, or rather, let's just call it 3x. Okay. You can use your base rules, but also another way, you can use the definition of a logarithm right now to switch things around, okay? Or let's, you know what, let's make life simple. Let's do it this way. Or you can do this. You so that the entire thing becomes the exponent. And because you're using the same base, and it only applies when these two are the same, this whole left-hand side is going to collapse and just be, okay? But I will tell you, the number one way that kids mess this guy up is that they're trying to do things, trying to do too much at once, okay? For example, if you had this, I'll do base 10. Let's just say you had that, okay? One way that some kids want to solve this is to jack a 10 under everybody. That's not correct. You cannot do that. Let me just make it a little bit nastier. There we go. Worse. Now it's worse. Okay? I cannot do this. That cannot work. You cannot jack a 10 under everybody, because remember, when it's not written, it's base 10, right? The rule states that you jack a 10 under the left-hand side and the right-hand side, not everybody individually, okay? Because remember, the rules for exponents are different than the rules of normal numbers, okay, or adding and subtracting normal things, okay? Instead, in order to play this game, you have to do it this way. Once you've combined it into a equaling a single log, then and only then can you jack 10 under both sides. That is the only time that would work. And then it collapses to 28x equals x, and x is equal to 0. Actually, you can't have it equal to 0. Now it'll work. Now x is equal to 1/27. Okay, because remember, x can't equal 0. Remember? I said x couldn't equal 0. And it's that if I plugged in log of 0, this right-hand side would not be defined. Okay, so that's another thing you have to check out as well, is when you get an answer, plug it back in and make sure that you're not getting something that is false. Okay, or, you know, remember when you were dealing with rational functions and stuff like that, and you had excluded values or holes and things like that? Remember when you got your answers at the bottom of the page, you had to take them back up, stuff them into the original problem, and make sure that they didn't, like, say, divide by 0 somewhere or something like that? Okay, that applies here. Whenever you have a domain that's restricted, like a square root function, or a rational function where there's some polynomial in your denominator, you always want to make sure that you're not dividing by 0 or taking the square root of a negative number, or in this case, taking the log of 0 or a negative number. Okay? So always check for excluded values. And obviously, if I went up in here and plugged in into all of those x's, I would be getting positive numbers in all cases, and I would be able to take their logs. Does that make sense? Okay? Who has no idea what I'm talking about? All right, last rule. This one is crucial when we get into calculus. This is the change of base formula. Okay. So, let's just say you were looking for a numeric value. You were actually looking for some crazy-ass decimal to be spit out because you're dealing with some word problem. Okay? How many years until there are 25 bears in the forest? Okay, well, fine. All right, bears grow exponentially, so we've got some exponential function in there, and, when we take the logarithm both sides, we want to find out some function of, say, years. It could be 5.5 years, 2.7 years. We need a numeric answer, okay? Well, our logarithm button on our calculator, there's only 2 logs that are given. One of them is base 10, and the other one is the natural log. It doesn't give me, say, base 7. Okay. Yes, there is math 0 if you go into the newer operating systems actually have a different base button. But when you're dealing with an algebra, you want to, say, combine logs of different bases. Okay? Trying to mush stuff together that normally wouldn't fit together. You do this. And presumably C is a nicer base, okay? So if you're trying to combine, say, a logarithm with base 5 and another logarithm of base 2, you would use this so that you could put them together, okay? For example, if you wanted to express log base 5 of x plus log base 2 of x, and you wanted to express that as a single term, okay? Remember, this is not an equation. We're not solving for anything. We're just combining. You would use your change of base formula, and you would use, let's keep life simple. Let's just put it all into, say, 10, or whatever else you want. Doesn't matter. And you see, now that everybody is of the same log, of the same base, now they can start working together. Okay? Just like unlike terms. You can't combine unlike terms. Well, now we can just get common denominators, mush all my fractions together, and move on with things. So, and now we've got a single fraction, and of course I can pull out a GC. And this upper fraction, this upper guy can be combined because addition becomes multiplication, and we wind up with addition becomes multiplication. And what is the one thing that I can do now to simplify? Can I do anything anywhere? What is the base of that log? 10. What did I say log base 10 of 10 is? What are your rules? Look at your rules. When I have log base a of a, what's it equal to? 1. And no, you cannot combine those terms in your denominator, and you're done. You see how it's a different kind of mechanical process. Okay? All right. Those are the 8 rules of logarithms. In fact, they all kind of boil down to just the definition of logarithms, but I'm going to throw you guys to the boards for a minute, and we're going to get some practice in. This episode of The Ronco Show has been brought to you by the 8 laws of logarithms. And the number 4.